And I'll hit the share and share screen. Boom. All right. Well, welcome to the final exam review session here. Do a little bit of a preliminary thing here. If anyone has requests for a particular problem or problem type, please don't hesitate to ask in the chat. So here's the material we covered since exam 3. We had mass, moment of inertia, rigid body, Newton's second law, rigid body work and energy, and rigid body impulse momentum / impacts. And here's on the equation sheet, here's where many of those things appear. Right here at the top, we find where the center of mass is. Here's the conceptual or the fundamental mass moment of inertia equation. If we want to have the radius of gyration, a reminder that that's a simple way of communicating the mass moment of inertia. If it's maybe a strange shaped body and we just want to give you one parameter, all you need to do is square that and multiply it by the mass, and then you get the moment of inertia. And if you want to put together the mass moment of inertia of a more complex thing, you can take different shapes. The important thing to use is the parallel axis there. Down here in the lower part, we have the equations for rigid body stuff, where we have Newton's second law. Remember that it still applies, but now we're going to focus on the center of mass. And we also have the rotational type of Newton's second law, where the sum of the moments equals the sum of the effective moments. And we say that because we can have some instances where we might want to take the moment about something other than the center of mass. So if it takes about, so let's say O, we have to remember that we have to take the I times alpha and also the mass times acceleration times the distance to the point about which we're taking. Things that we add to or changes that we make to the work energy equation is that we can also look at the work in terms of a moment times a change in angle. Kinetic energy is no longer just 1/2 mv squared. You also need to include 1/2 I omega squared. Notably that you could also use the parallel axis theorem if it's a constrained motion and do it about like a pin joint right there. So you could do it in one step if you do the mass moment of inertia transformation. Want to extend the impulse and momentum for translation into a global one, where we say that the entire momenta, that's both the translational and the rotational, before an impulse is applied, plus the external impulse, will equal the momentum after that event. So we have three states or three elements right there. If this system external impulse is 0, or it can be ignored, let's say, then we can have the conservation of momentum, whether that's translational momentum or angular momentum, which is defined by I omega. And so here is the impulse momentum. It says for particles, and that actually is kind of true. It's actually for particles and for rigid bodies, I should point out. But most of the time we're associating with, we didn't really cover chapter 14, which would have talked about a bunch of different particles together. But it's really that chapter 14 is really a precursor to rigid bodies. It's sort of like a in-between step. Notably, this version of the equation has an error. This should be R crossed with the moment, the inertia, excuse me, the momentum. R across the momentum, so that they have this backwards. But we don't usually, we haven't typically been doing that with vectors. But if you actually to run the vectors correctly, you would use this one crossed with the other. So I have a request from Dylan for spring 2014 N2L eccentric cylinder. Is this the one right here that you're referring to, Dylan? Okay, so let's take a look at this one. My good friend Alicia Garcia wrote this problem. So we have this eccentric cylinder. So it's going to pivot about a point that isn't the center of mass. And if the magnitude of the angular velocity, omega, and its angular acceleration, alpha, are respectively 10 radians per second and 2 radians per second squared at the instant shown, draw the free body diagram and inertial diagram at the instant shown, write the equations of motion, which I don't always use this phrase, but those are the equations of motion. That's the right phraseology for Newton's second law equations. For the x direction and y direction, and determine the reaction forces at O. So let's take a look at that. And I will pull up no, I'll pull this over here to the other side. Come on. Get back. Get over there. Get over there. For any of you that, I guess I point out that I had COVID, right? Boy, what a good night's sleep will do for you. Oh, I needed some sleep. I feel much better today. So there you go. All right, so, see, oh, I guess I have that up there. I'll move him over. All right. So this is my S14, and I'll draw out the problem. And let's see, I guess this is 2 inches and this is 4 inches, and this thing weighs 40 pounds. And right now it has a alpha here and an omega there. So some of the first things I might want to do is I might want to find out from the kinematics what the acceleration g with respect to O in the normal direction. So I'll go omega squared times r g with respect to O. And what did we say omega was? We said it was 10 radians per second, and alpha is 2 radians per second squared. Oh, she's done that for me over here. Good. So we had 10 squared, and I think it's better to change this at this point into feet per second squared, right? So that's going to be 2 over 12, and of course she has the posted solution here. She has her own way of doing things, which I think is fine, but I just wouldn't do it that way. 16.67 feet per second squared, right there, right? So didn't necessarily have to do that first, but I decided to do that first. So I'll draw my FBD, my IBD. And let's see, we're gonna have supports right here, and we've labeled that O. So this is rocks, and here's Roy, and we're gonna have our weight happening down right here. Interestingly, that she writes it MO. That's a weird way to write the thing down. That's okay. Even though the thing is 40 pounds, and then over here we have at the center of mass, yeah, kind of drawing it right there and right here, we have MAX, and here is MAY. y, and then right here we're going to have I alpha. Now we always have a choice when approaching this. We could remove this right here by changing that, but let's just leave it. Let's just leave it alone. And so, well, first off, this was given to us. So I think the nature of this problem could be, I don't know it to be true. I would assume that she had checked on this, but I guess what you have to say, by the way, I didn't read the problem all the way through correctly. Okay, I see. There is an applied moment, and this is in the horizontal plane. So I messed something up. I didn't read it carefully enough. That's a danger. There's no weight right here. This is in the horizontal plane, so I should have written that out. Horizontal plane. And as part of in the problem, it does say that there's an external moment. I see. So there's a moment about O that's being applied. So we have to kind of figure out what that moment about O is going to be. So that's what the nature of the problem. Okay, should have read that more carefully. Danger, danger. Don't be like me, kids. So like, go ahead. No, I guess that was not a.
Dr. Deal, I am trying to connect to my headphones and it's not working, so I didn't mean to blurb.
No problem. No problem. Okay, so following the directions of the problem, I guess is what I should have done, is to draw the free body diagrams. Okay, so I did that part, and write the equations of motion in the x direction and y direction. So I should just follow directions. So mass times acceleration, and in the x direction. So what we have is we'll have rocks. I drew it positive because I wasn't quite sure which direction it was going to be necessarily. And then all I had right here is in the, excuse me, it has to be equal. Dummy. Right hand side. MAX, which we happen to know is aligned with this right here. So we could go that rocks is going to be the mass, which is 40 over 32.2 times 16.67. And I hope I got that right. I'll go 40 times it and 32.2 divide. And I should get 20.7. Oh. And these are pounds. And then sum of the forces in the y direction, mass times acceleration in the y direction. And simple enough, because so we have Roy, that's the only thing we have in there, and we have it's going to be equal to MAY. And also from kinematics, maybe we should up above, we should have also noted that the AG with respect to O in the tangential direction was going to be alpha R G with respect to O, right? So we could have said 2 times 2 over 12, which would have been 4 over 12, which is to be like 0.333333 feet per second. So Roy is equal to 40 over 32.2, 0.3333. So we get 32.2 and multiply it. And I think we're only get a small 0.414, call it 1, pounds. And then let's see, lastly, sum of the moments about O is going to be equal to I alpha, but also the effective moments, right? So actually, I should write, if I'm going to write as a reminder, the sum of the effective moments is going to be I alpha plus M A, call it Y, times the distance R G with respect to O, right? Because that's G and that's O right there. So we had that MO, which is an effect, which is a moment they tell us is externally. That's the thing that's causing it to be alpha. The moment of inertia of this, did they tell us a disk? They didn't give it to us as a disk, right? They just said it was a disk. Yeah, it's a cylinder. Okay, so any type of cylinder, maybe we should have written out the moment of inertia somewhere up above. 1/2 mr squared, and so that's 40 over 32.2, and the R of this is 6 inches, right? I think, yeah, the radius is 6 inches, so that'd be 6 over 12 squared, and 40 over 32.2, 5 by 2, and then 0.5 squared, which you should be able to do in your hand. And we get a 0.1553, and these are slug feet squared. And so, okay, so on the left-hand side, we had M. That's the only thing right here because we're taking it about here. So both of those get canceled out because we're taking the moments about that point. And on the right-hand side, we have, oh, and by the way, these should be negative, right? If we're going to use the convention that we usually do. And 0.1553. And we have the alpha we were told, so that's going to be 2. Right, but we also need to have this guy right here, so that's going to be minus, and the mass is 40 over 32.2. And the acceleration in this y direction, we already found it, of 0.3333. And this r is 6. No, not 6. It's just 2. It just is the distance to the center of mass, right? From the point that we're spinning about. So it's 2 over 12. So MO should be, if I did that right, 2 times and 40, 32.2 divided 0.33333 times 2 divided by 12, add them together, and I get something. Oh no, I get the same thing. Okay. So 0.3796 foot pounds, or pound foot, whatever you want to call it. And I believe that's the answer. Okay. Is there any questions on that? All right, we got through one of them.
I have a question quickly. So in this problem, it tells you to use Newton's second law. Say that it didn't tell you to use that method. What would be the first thing that would help you identify that this is a method you can use Newton's second law to solve this?
Excellent question. I probably think that the angular acceleration would be the number one key, right? Anytime that they get, because the way that they set this up was with that they gave you the, most of our problems have been where we knew the forces and we wanted to find the motion, but here instead they gave us the motion and we had to find the forces. So the fact that there was the acceleration there kind of gave us, and the fact that it was an instant in time, right? So that's a really good question. And I think a good thing to think about, right? That we don't know anything about a later state, right? So work energy usually is between two states. So we would have known like at least maybe a change in position or something along those lines. Also, impulse and momentum, usually there's some amount of change in time would have taken place, or there's like a collision or something like that. So so all of those things were kind of like to be the detective to figure out like what's the best way to approach this thing. So I think because of that you had to use Newton's second law.
Thank you.
Do we have? You're welcome. You're welcome. Do we have a request for another? I could just pick one out if you'd like. Whatever you'd like to do. All right. Let's see. Bryant, thank you. Can we do Newton's second law with polar coordinates on page 11? You're gonna have to help me out a little bit. I don't quite know what page numbers they are, although I have them as slides. So it might be this one. No. Polar coordinates. I'm looking for one with polar coordinates. Is this one right here? That one. Okay, cool. All right, so let's take a look. Read this carefully. Come on. There we go. All right, so I wrote this one. A disk rotates in the horizontal plane about a vertical axis at the constant rate of theta dot 15 radians per second. Slider B has a mass of 230 grams and moves in a frictionless slot cut in the disk. The slider is attached to a spring with a spring constant of 60 newtons per meter, which is undeformed when the radius is equal to 0. Okay, right. Knowing that at a given instant, the acceleration of the slider relative to the disk is negative 12 meters per second squared, and that the horizontal force exerted on the slider by the disk is 9 newtons. Okay, determine at that instant the distance r and the radial component of the velocity of the slider. So what I'm trying to do here is to kind of throw the test taker, if you will, out of their comfort zone and try to like pick this apart step by step. It is a challenging problem in the sense that like, oh, we haven't seen this one before, but you'll see that it's just really just kind of methodically going through and picking out what you know and how it's arranged. So this is not a rigid body problem, by the way, so I would point that out. This is really a particle problem, if I think is how I would call it. Let's see if I'll just keep it the way it is right here. Let's see. So I'm going to draw the problem a little bit because this is my method when I'm working through things. Is I got to think my way through by making this diagram. And so as I'm going along here, it kind of helps me to organize what I'm going to do. And as I'm going through here, I generally will start to have a better idea of how I'm going to approach the thing. So writing down the givens and that kind of thing is it's almost like a comfort blanket, right? A security blanket. Let's see. So the mass of B is going to be, I'll call it 0.23 kilograms. And K is 60 newtons per meter. And it's undeformed when radius is there. Okay, that's good. And we note that this thing's right here, it's R double dot is going to be negative. So that means that it is going towards the center, 12 meters per second squared. So even though maybe on my solution, And my solution, I drew it down here at the bottom. It doesn't really matter, but I'll keep it consistent here. I drew the disk as a dashed line, but I don't really need the disk as part of this. This is really a particle problem because I have that little dude right there. This is the thing we're focusing on. And you could take a look at the forces that are going to be on this. Well, one is going to be, if you think about why this little piece is moving, it's because if he's going counterclockwise, so the slot he's sitting in is pushing on him. And I call this the FD, so I think it's for the disk. This is the force of the disk onto this little slider thingy. We also have the force of the spring, and because the spring is on the outside right here, it's going to be like it's generally going to be compressed, right? I don't know for sure that it's going to be in this direction. It could be pulling onto the thing, but I think because it's undeformed when it's at the center, it's probably being pushed out this way. So I'm going to call that FS right in here. And over here, it's going to, well, we'll just assume in a positive direction. So, this is polar coordinates. So R should be, ER should be in that direction. And E theta should be in that direction. So, but I know that or I'm pretty sure, a lot of times that signs can be kind of dangerous, but I'm going to go ahead and put them in there, right? M, and so this is going to be A theta, and this is going to be M A R. So I say the sum of the forces in, let's say, the radial direction, it's a good place to start, it's going to be equal to the mass times the acceleration in the radial direction. And as we drew, that's going to be positive to match up with this right here. So it's all about the spring force and this guy right here. So we don't know how much this thing is deflected. We don't know what R is. That's the thing we're trying to find. But we do know that the spring force is really going to be, because it's going to be the deflection, but the deflection is, because it's 0 at here, deflection equals R, right? So we can make that statement here. And it's coming in the negative direction, so we could say that we have negative KR, because this is the positive direction. And now we're going to have the mass of the thing, but now we're going to have the acceleration in the radial direction. And remember, that's going to be R double dot minus R theta dot squared. Now, because I drew it in the negative direction here, I really should make this negative. I think actually I'm going to mess things up by having drawn it in that direction. It really is probably, the acceleration probably is in that direction, but it's better, I think, to make this consistent by not drawing in the negative direction, because I'm likely to get a negative answer to the thing. So it's just negative and negative and negative. So it's probably best that I would have drawn this in the positive direction. So plugging my values into this, I get 60 R equals, and the mass of the thing is 0.23, and I know that it's gonna it is actually moving negative 12 right here. So that's already see, that negative is taking care of the direction of the thing. So I should, keep it consistent. That's why I don't use the negative right there. And then R that I don't know, and then I have 15 squared. So if I do all of that, I should get a radius of 3, 3, 4, 5. But let me double check. I think, well, there's no reason why it shouldn't be. But me in the past might have messed the thing up right here. I think I could just trust myself. And then knowing that, I can now take the sum of the forces in the theta direction equals mass times the acceleration in the theta direction, and theta is positive in that direction. And we're taking a look back up at this. We see that this is going in the positive direction, FD, and that's something we were told, right? We were told what that force was. Let me double check here. Yeah. So we were told somewhere up here, I should have written FD is equal to 9 newtons. And there's no other forces in that direction, and they're going to have mass, and the acceleration here is going to be r theta double dot, and plus 2 r dot theta dot. But good for us is that that's going to be 0. So we didn't actually need to know that r, but it would have been that would have been if you had been asked like maybe a more difficult question would be to find out what r dot was. Give you all this information and then just ask you what r dot was, and you would need to go through this process just to get to r dot. But yeah, anyway, so this is 9 and 0.23 and 0 here, plus 2 r dot, and then 15. So we end up with an r dot of 1.304 meters per second. Let's see. So I have a request for a page 5, this guy.
Yes.
Okay, yeah. I tried to do a kitchen sink problem here. That's how I think of it. Where we have a 60-pound wheel with a radius of 2 feet, rolls on hubs. So that might be hard to picture what that looks like. So maybe we should draw a sketch of what it looks like from the front. Without slipping, under the action of an applied cable, and Layla is giving her opinion of the mailman coming by. With a tension of 16 pounds, and there's a spring at the center of this thing of 12 pounds per foot, and the cable unwraps from the wheel as it rolls. The radius of gyration of the combined wheel and hubs is 8 inches, and the wheel is released from rest when the spring is unstretched. So we want to. Oh, and this was long ago when I wrote this. Wow, so many years ago. Like 8 years ago. And the back then I often would ask people to do things. I don't do that anymore, where I ask for one step at a time kind of thing. So let's see. Dog, you are a mess. She's cute though. She's a very cute dog. I should invite her to come over here and see what she has to say. She's very upset by male people in general. Could be. I think she doesn't like FedEx. She really doesn't like FedEx the most. It's very disturbing. The other day, one FedEx person left a dog biscuit on top of the box that they left behind. I thought that was kind of funny. Because I don't know, they wanted to win over her favor. But if she had ever caught, I don't think she would do anything. She would just lick them and sniff them. It's more like she just wants to be loved by the package delivery people. Okay, so let's see, what should we do? We have a find the length of the cable measured from A that is unwrapped from the wheel after it has moved 6 feet down, right? So this thing has moved 6 feet, and we want to find out how much length of cable is going to move. Well, so that means that we're going to have a delta theta of this piece right here. So this thing's going to roll and produce a delta theta, which is going to really be how, and so we kind of zoom in and ask how many, I think of them as circumferences, if that's a way of thinking it, right? So you can like actually kind of see as this thing is moving down the slope, how many, what's the angular displacement it will make by moving 6 feet. So what we really have is, let's see, what did I use as my, I call this delta S, by the way. So we have delta S divided by that little radius, which I didn't give a name for. I guess I called it hub in supposed solution. So that was 6 feet. Hey, you okay? All right, don't worry about it. And what did I? 6 inches, right? And divided by 12 right there. So I think we're going to end up with 12, right? We're going to end up with 12 radians. And so now we figure out, well, what's the length of the change of this right here? Well, that should be delta theta times the radius of the big wheel, which, what did I call that here? I just call it wheel. Or 12 radians times 2 feet. Sure. So it was 24 feet. That's how much cable went out. The external work performed on the system by the cable. So that could be done in one of two ways, right? So the main way to do it, I think, given the fact that we have this tension already, I say we just go F times L, right? Or delta L, I guess I decided to call this delta L. So let's go delta L. Change in length of this cable that would have to be unwound as we're coming through here. So I would actually tell you the truth. Ted Deal these days, let me think about this. I think I made a mistake right here. I am weary that I made an error that didn't get caught by myself or my colleagues, because not only is this going to be the force times the change in length of this thing, but I think we should add that delta S in there personally. Because if you think about it, right, if you draw a little tiny picture of this thing that's happening right here, and how far is that force going to go, right? Well, not only is it going to go the change in length, right? If that was the change in length, it's also going to go the delta S that the thing has moved. So I think this is, I'm riffing here, but this is my thought. I believe that it's necessary to have them back up. What do you guys think? Do you think that's true? And if you start picking it apart, anybody have an opinion? What do you think? You want to judge me for me from 8 years ago? Which do you think is true? Should it be delta L, or we could take a poll?
I thought that the delta S would be incorporated already in the delta L.
I think that's what I had thought previously, so I'm not going to try to, I'm not arguing. I'm just saying that, like, let's say this thing was sitting still, right? And just moved delta theta, right? Let's say it could slip, is what I'm saying, right? So we'll just say that the delta theta didn't come from here. The delta theta was just a thing that happened to move that amount. It would only get to right here, right? Like if this point it indicates where it started right there, it would move this distance if this thing was just spinning. But it's also, this thing has also moved down delta S, right?
Wouldn't delta
So
S include delta L? So we'd have to like subtract delta L from delta S?
I don't think so, but like I'm trying to, like I'm almost like telling a story, right? So that I give like a what if this thing was, if this thing was fixed somehow, like right here. So it is, and it rotated 12 radians without moving down the slope. This point right here would then be right there, right? Which it would simply be delta theta times the radius of the wheel, right? It would be that radius times this would be the amount of cable that had been pulled out. But it's not pivoting right there. It's moving as it goes along. So the point that you grabbed up here along the way is right there. So it's the force through the distance that has actually occurred onto the piece, I think. But I see what you're saying. But I'm fairly convinced I'm correct on here. Not a great thing for a student to hear of a professor who's arguing with himself. But I want to be honest as I pick the thing apart, that I do think that this is the correct amount of thing. It's really the motion that has happened, right? That the entirety of the motion from where it starts to where it finishes, regardless of how that occurs. So I think it's going to be the 24 feet plus the fact that it's moved 6 feet. So I want to ask Dr. Orlip or Dr. Rico or Professor Obst what their opinion is. So that, but then anyway, I'm revising this for the time being as being this, but interesting. I wonder if any students picked up on this. All right, so the next stage that I'm asking on that was the potential energy, which is both gravitational and elastic, of the system at state 1 using the datum shown as the reference, right? So yeah, okay, so in here I told you what the datum had to be. So we're starting out there at 5 feet. And this is a method. Most of the time I probably would pick the datum at second state, but I told you what the datum should be. So we'll just go ahead and say, well, right here is 5 feet, right, onto the thing. So the potential energy at state 1, is going to be mg h1 plus 1/2 k del 1. And do they tell us in the problem? I'm looking to see where they tell us. Oh yeah, okay, so it's, I think in the problem says that it's unstretched. Oh, yeah, this right here says that the spring, when the spring is unstretched. Okay, so I happened to put that in there as a placeholder, but it was 0. So we have that this is 60 pounds, right? This thing is 60 pounds. So that's both M and G, right? And 5 feet. So that's an easy 300 foot-pounds. And let's see, the next thing we were asking for was the potential energy and gravitation, so gravitational elastic of the system at state 2 using the data reference shown, right? So this thing was at 30 degrees. So the potential energy at state 2 was going to be mgh2 plus 1/2 k del 2 squared. And so once again, that's going to be the weight is 60 pounds. So that's both the M and the G. The H is going to be 5 minus, so it has moved 6 feet, but we take the sine of 30 degrees. I think I did that right. Yeah, so that should be, this ends up being 2 feet, by the way, if you wanted to check. And then plus 1/2, and the spring constant is 12, and the distance was 6 feet that it moved. So the answer here is 300 and, whoop, did I do that wrong? No, 336. 336 foot-pounds. And let me take a look at this right here. The kinetic energy of the system at state 2. Really are asking this thing one step at a time, right? So we have KE1 plus PE1 plus U12 is equal to KE2 plus PE2. So we have 0 plus potential energy at state 1. We said it was 300. The work, I'm revising it. I've changed my mind, and it's 480 equal to KE1, which is what we're trying, KE2, which is what we're trying to find in this problem. And then potential energy, so here 336. So KE2, our new value, is going to be 300 plus 336. So we subtract that out. And I say that it's 444. And now for the last part of this, we need to have both of the, so the kinetic energy at state 2 is going to be 1/2 I
Dr.
omega
Gill,
2. Yes, yes.
why didn't you consider the moment of inertia in the kinetic energy at state 1? Dylan had asked that.
Well, it's starting at 0, right?
Oh, wait, sorry, I'm rereading his question. Why don't we have to consider moment of inertia for this problem in work and energy?
Well, we are right now. We're at kinetic energy state 2. We need to have that's when we need to have the kinetic energy. That's where we need mass moment of inertia.
Okay, thanks.
You're welcome. Something I could have done up earlier, and I meant to, so we'll come back to it here in a second. But I do want to talk about. I do want to mention that we had another choice to make up here. I meant, I got distracted by this thing right here, but we had some amount. Okay, so actually, this is an interesting thing. So maybe I do want to consider that delta S. Let's revisit this up here, but we'll come back to this right here. This is so just we'll hang on for a second. And but let's see, we need I. I didn't get I. We need we got the radius of gyration. I like to go M first. Sorry, radius of gyration was given. So we had 60 divided by 32.2, and radius of gyration, I believe, was 8. Is that true? 8, yeah, 8 inches. So over 12. So we end up with 0.8282 slug feet squared. So 0.8282. It's a decision on whether we want to solve for the velocity or omega. We were asked for velocity, so it's oh, I see what I did right there. Okay, so we know so a little bit of kinematics over to the side, just a small amount. We know that the velocity is going to be related to the radius of the hub. I think it's the hub. Should be the hub, right? Yeah, hub times omega. Therefore, we'd have omega is going to be equal to the velocity over the hub, and that hub is only 6 inches, I believe. Yeah, 6 inches. So that's 6 over 12 right here. So what we really find out, we get 2 times v. So inside of here, we're going to get 2 times v2 squared. We'll place it in there. And then 1/2, and then the mass is 60 divided by 32.2. And I don't need a parentheses. I just need a v2. And did I bother? Why did I solve it this way? Okay, so this right here actually equals, well, I'm saying it equals the 444, but now I'm gonna question myself here in a second, but let's just keep going with it. So all of this together, 0.8282 divided by 2, multiply it by 4, and then have 60 divided by 32.2 divided by 2, and add them together. So we get like 2.588 v2 squared. So if we set 444 equal to 2.588 v2 squared, v2 is divided square root 13.10 feet per second. Okay, and I think the last part of the thing asked for the omega now, which is sort of simple, I guess. But I think my thought process when writing this problem, to be clear, was I decided to make every one of these things 5 points because there's like 7 things. I think that was like my thought process. It was weird. I don't like that anymore, but it's okay. So I said that yeah, omega, which is going to be 2 times v, so 13.10. So we ended up with just 2 times that, or 26.20 radians per second. But let me go back, because this is, of course, I've just on the fly decided that I thought this delta S should be in there. But let's go for a different approach, because we can have a different thing here, right? We could also say it's the moment times the delta theta. And that moment should equal that tension force times the radius of the hub. So that would actually make my original one correct, right? The moment that's being placed onto this thing is that tension. Yeah. Interesting. And I can't think of a reason why this wouldn't be true. That we're applying an external moment, which is essentially what we're doing here. We're taking this force. Oh, here it is, right here. Yep, it is not that. Okay, there you go. Yep, got it. I'm correct. I was wrong in the past, but I'm correct, right? Because so the moment that we're actually placing onto this should be thought of as being about this point, right here. Is that true? Whew. I'm trying to decide if that's true or not. I think so. 16 times R2 plus 6 over 12, right? So 16 times 2.5. So we get 400. Is that right? That doesn't seem right because we're about to multiply. That's going to be a lot. 16 and 2.5. I'm going to try that again. 16, 2.5. Oh, that's just 40. Okay, 40, not 400, dummy.
Would you be able to just move your sheet down a little bit?
Oh yeah, sorry. So we'd say 40 times 12, right? So you get 480 foot-pounds. Yeah. So I think it's all about whether I decide that the moment should be about the center of the thing or whether it should be about the point of contact. And I think it should be about the point of contact. I don't know. I'm sorry if that's not that's not a good feeling to have that as as we're starting during a review session. But it is sort of the nature of dynamics that you could sometimes have discussions, should we say, with yourself and with other engineers to try to decide which is the appropriate thing. So then the next stage would be to go ask one of my colleagues their opinion. We could have a discussion about it. But anyway, I apologize for causing trouble. Can we pick another problem to look over? I personally wouldn't grade. You know, if someone had made this mistake right there, I would obviously probably not count points off of the thing. All right, so let's see. Can we do one acceleration of rigid body review? All right, so let's see. I have we had one this guy right here, and yeah, so we hadn't done one like this too often where it was actually the slider that was moving. And so what we're trying to do is determine the acceleration of the wheel at this instant, right? So we want to find what the angular acceleration of this wheel is going to be because of this. And I don't think this was actually an exam problem. Maybe, you know, I bet it was. It looks like it was put together like as if it was from a good friend, Sean Munnis, former Tesla employee. I don't think that's a big deal or nothing. Okay, so reading this thing. At the given instance, slider B is traveling to the right with a velocity and acceleration shown, right? So 6 inches per second and 3 inches per second squared. Determine the angular velocity of link AB using the method of instantaneous center. Hint, what are R, A, I don't like, oh, I just noticed this is, this thing isn't pure translation, by the way, so that makes this problem too easy, but that's okay. That happens a lot with exam problems when it comes to the acceleration one, that we overly simple, we make it simplified. So it might be better to actually do another problem in addition to this. We'll continue with this one, but just note that this the angular velocity of this of this bar is going to be 0. Therefore, it's going to simplify the acceleration analysis, and I'll show you why that is here in a second. But see, this is a 5 inches, can barely read that radius. And you can see that this thing is aligned like with the bottom of it. So this total distance is 10 inches, and this is 20 inches right there. So let's take a look at the problem here. So I'll draw the thing out. And let's see if I can draw this thing correctly. I'll get him out of the way. So the bottom of this thing comes like to right there. My circle isn't going well. It's getting eggy. Yeah, that was not a great demonstration of circle drawing ability. Oh, and my brain's not working. That doesn't go there. It's much smaller than that. Oops. What can I say, man? I got COVID, right? Is that my excuse? I can make that excuse? Not for much longer. The doctor gave me that Paxlovid stuff, but I didn't get it until this morning, so I'm already feeling better. So I don't know if it was worth it. Doing it anyway. I know you're excited, but I didn't know about that. There's 20 inches, and this is 5 inches. And so what were these values right here? Where'd you go? Nope, my mouse is on the wrong screen. Okay, great. And so this is acceleration of, I guess this is B, that's A, and we'll call that O. And the acceleration of B is 3 inches per second squared, and the velocity B is 6 inches per second squared. And so some of the big idea we do with well, maybe we should do a little geometry first. So maybe we want to find, let's see, you go from observation, that should be like in line with this. I just didn't draw right. So we could say that's theta right in there. So theta is going to be no, not inverse tan. Let's make it hypotenuse. So it's going to be this inverse sine of 10 over 20, right? And that might make it 30 degrees. Does it make it 30 degrees? Probably makes it 30 degrees. I think so. Yeah, so that's 30 degrees. That should be obvious to anyone. 30 degrees. Okay, so to do the velocity analysis of this body right here, and And if you try to do the ICR of this thing, you would say, okay, well, the velocity is going in this direction, so the line for the ICR is in that direction. Well, on the wheel, the velocity needs to be in that direction, so the line for the ICR is in that direction, and therefore ICR is infinite, and omega AB is 0, right? Because these are parallel lines that could never have an ICR. So this thing at this instant is in pure translation. It's really kind of, you could just kind of think of it in another way, is that it has just changed its direction of rotation, right? So if if you're looking at with a connecting arm, you're having a motion that's like this right here, right? So he's rotating in this way, and then he begins to rotate. So he's rotating this way, and then he begins to rotate that way, right? At some point. So this is like the change point of his angular velocity. Therefore, it's 0. He will, and you'll know that it'll have its maximum angular acceleration right at that point too, because when they're one's at one's at 0 and the other one's at a maximum. So that makes it a little bit easier because we don't have to worry about acceleration onto the thing. But continuing with our velocity analysis, that means velocity of B equals the velocity of A, right? And you could prove that by doing a 3 diagram method if you wanted to. I'm making the thing look like too much like 45, which isn't very good. But if you do a 3 diagram method of this thing and you place, I drew the velocity the wrong way, didn't I? Yeah. Here's the velocity that we know right here, the velocity of B. And you take, well, we're going to say the velocity of A is right there. Take the known one and apply it to right here. And then put the thing up. And this omega right here is equal to 0. Therefore, this VA with respect to B is equal to 0. And so therefore they have to equal each other, right? That's the conclusion that you would have to draw. But I think you can believe it. But if you needed to prove it to yourself, you could make that diagram. So here's the velocity of A. And so now we're going to have omega OA, or we call it AO if you want to. And so we'll say the OA is going to be the velocity of A over the radius of A. So we can keep it in inches because it was already in inches. So this was 6 inches per second. And this was 5 inches. I think we could say that. Oh, whoa, wait. I just made a mistake. Damn. It should be to right there. Ah. That stunk. Should be, it should be to the spot right there, right? Let me double check. Ooh. He is saying that he thinks it should be to the center. I think he's incorrect. Because we should have, this should be connected to the, because, so is it moving without slipping? Oh, no. Yeah, no, I'm sorry. My bad. It's not on a surface. It's on a pin. Oh, COVID brain. I was right. My bad. Sorry. So 6 inches per second divided by 5 inches, and we get 1.2 radians per second. Yeah, that makes sense. Why was I thinking it was a wheel? Oh, maybe I should not have had this session today. we'll just try to go with it. Okay. For the acceleration of this wheel, right now, we should start with something that we know. Well, or we can go ahead and get one of the accelerations. We don't know this acceleration. Let's call it A tangential, but we can find the acceleration in the normal direction. So the acceleration of A in the normal direction is going to be that omega OA squared times its radius. And now we should probably, actually, I guess we could do the whole thing in inches. It doesn't matter, right? We don't need to convert it into feet. There's no reason to, because it's only if we're doing one that requires Newton's second law where we have to use slugs. You have to use feet with slugs, but we don't have to. If we're just doing acceleration, we don't have to do it. Sorry, 1.2 squared times our 5, right? So we should get like 7.2 inches per second squared. All right, so I do my acceleration analysis, and it's a better idea to try to draw this thing with my 3 diagrams. And I don't know this acceleration, but I do know this acceleration. And I also know this acceleration. So I have the acceleration of B, acceleration of A. I guess I'll call it normal. I'll keep calling it normal. Acceleration of A, tangential. So because I fully know this spot, I'll use him as the reference for translation. So acceleration of B, acceleration of B. That means I'm going to pin it right here. And I don't know the angular acceleration, but I'll guess in a positive direction and call it AB. And so that means this guy, acceleration of A with respect to B, tangent direction. And I think the angle I need to use for this is that guy right there is going to be the same as that angle right there. All right, so that's theta. There is no acceleration in the normal direction. I'll draw it in here. So we go acceleration of A with respect to B in the normal direction, but that equals 0 because this equals 0, right? And so that's the thing that makes this is the reason why this makes it just a little bit more simpler. So let me take the thing that I know is in the y direction. I know this spot right here, right? As opposed to some other problems where we set it equal to 0, or we looked for the thing that was 0. In this case, we'll look for the thing that we know. So we're writing out the acceleration of A is equal to the acceleration of B plus the acceleration of A with respect to B in the tangential direction, acceleration of A with respect to B in the normal direction. And we'll start with the y direction. And we know that this is going to be a negative 7.2. It's going to be equal to 0 here, right? There's nothing in the y direction there, so that makes that a little bit easier. And then this is going to be a negative, and it's going to be that alpha AB times the length, which is 20 inches. But then also we have to make sure that it's only the y component, so that's going to be the cosine of 30 degrees. And so we will get the alpha AB is going to be 7.2 divided by 20 and divided by the cosine of 30. And so we should get 0.4157. And it's positive. So this guess that we made up here was the correct guess, that it was a counterclockwise. And now in the x direction, I drew it as if it was positive. So I'll just keep that way up here. I drew it as positive. I'm sorry, not here, but I drew this as positive. So let's see. We go here equals positive acceleration of v, which was given as 3 inches per second. This one is negative. So we use 0.4157 times the length of 20, but now times the sine of 30. And so let's see, times 20 and sine of 30, which is 0.5 times there. So we end up with a negative value. So it turns out, because we're going to have, right, so I end up with a negative 1.157 inches per second squared. And then lastly, we come back up to this guy right here. And we know that alpha, whatever we want to call it, AO or OA, AOA is what I called it before, is going to be the acceleration of A with respect to T divided by R. I just called it RA before. So 1.157 divided by 5. And so what we end up getting is 0.2314 radians per second squared. And up here, we drew it to the right. It's actually to the left, which means that it's a counterclockwise rotation. Let's see what my idiot friends are doing. Yeah, okay. All right, so do we want to do another one that's more kind? Can we do one? Any more suggestions? We had any of the requests, suggestions, affirmations, intergens?
You had mentioned in class that for the impulse momentum problem, it would be more like a fixed problem, right?
Yeah, generally speaking, it's tough to make one that doesn't take too much time. I don't think I even have one that's not a fixed impulse momentum problem.
Yeah, that's what I was just wondering.
Like this one is not a fixed one, right? But I think we almost did this problem. I'm not sure even where this one came from right here. Why is this one even in here? Maybe. Yeah, so this one right here is a non-fixed one, and I don't know if I didn't post the solution to this one. I'm not sure what me in the past why that's even in this slideshow.
Do you know what page that is on? Because I don't see it in
I
my
don't.
kit.
I don't think it is on any page. And it looks very old too. I'm not sure where it came from.
I know we
That's
did
not it.
a problem like that in class as well as for homework and stuff.
Yeah.
But
I think maybe I just wanted to include it. You know what? I can solve it. Let me just watch this. Let's move him to the bottom. Get him out of the way. So I think I'll just hit him back. Control X. Ooh, put in other things in here. Okay, so I think these guys come from must right here, from must problems. Here's ones we could try. None of these are impulse momentum problems, though. This is really similar to what we just did right here. Well, this is very similar to what we did. Oh, they have an angle right there. This is, I think, Missouri University of Science and Technology. They made an acronym out of it. So, got any requests? A type of problem? We could try really hard.
There was another problem with work and energy. It was the Boeing thing on page 12.
Boeing thing. Yes. So this is a particle one. So they have a 4-pound collar, can slide without friction along a horizontal rod and is at equilibrium at A. When it is pushed to the right 1 inch and released from rest, the springs are deformed when the collar is at A. Okay, what does that mean? The springs are undeformed. That makes more sense. The constant for each spring is 2,800 pounds per inch. Determine the maximum velocity of the collar. All right, so the maximum velocity of the collar, where do you think that's going to be? That's a good question right from the start. Anybody want to hazard a guess where the maximum velocity is going to be of the Boeing thing? Let's see. I can't see. Let's see. Yeah, when it's at A. Well, not exactly once it's released, because let me. I gotta see the picture of the thing as I'm doing this. Yeah. There we go. All right, so I guess we can draw this as one thing. Attach right here and right here. We got a little collar going on. Okay, so what we've done, it's almost better to make a little sketch of what it looks like. It does help with, it helps with the geometry a little bit, right? So it has moved over right here. So we'll exaggerate. So it has moved over to like right here. And it has potential energy from this being in compression and that being in tension, right? So I didn't put my 8 inches in here and 8 inches in there. So the maximum kinetic energy occurs when the potential energy is at a minimum, right? So the potential energy is at a minimum at A. So that's probably the way to think your way through when the thing is going to be at a maximum. So it's going to be a maximum at A. So one of the first things we need to do is figure out what the deflection of each spring is going to be. So I guess I'll call the springs AC. And well, first I need the length of each one, right? So that's sort of an important thing. I think this is a 3, 4, 5 triangle though, right? So this should be 10 inches. The undeformed length of each spring is 10 inches because it's 6 and 8. So AC, because this is A, C, and B, is going to be 10. I don't know if I'm going to go minus. Am I going to go minus? Yeah, I go minus. Be the square root of 6 squared plus, now it's going to be 7 squared, right? So that should be minus 10, 0.7805 inches. And then for BC, it should be square root of, now this is going to be 9 squared, right? So because it's moved over. So this is 9 right here, and that's 7. So it's be 9 squared plus 6 squared, and then minus 10. So what, 81 and 36 and square root, and then subtract 10. So we have 0.8167 inches. And notably, this is actually compressed, where this one is in tension. But it doesn't matter when it comes to potential energy. So we write out our main equation so we can start thinking about populating it. And I'll call this state 1, and this is state 2, where we know that's going to be, the PE is going to be 0. So it's released from rest, but I should go down the list like I usually do. I like to do that better. So KE1 is equal to 0. PE1 is 1/2 K del AC squared plus 1/2 K del BC squared. It's a good idea to turn these, I guess it might be easier to do it after I get done finding the potential energy in inch pounds, then I'll turn it into foot pounds. Because otherwise I have to turn the K into foot pounds and then turn the del into foot pounds. So I'll just do it after the fact. So 2,800, 0.7805 squared plus 1/2 2,800, 0.8167 squared. So let's see. Square that. Square that. I could just add them. Yeah. 2,800. 1, 2, 1. Okay. So I get 1,000. Excuse me. Oh, 1,700.
Lost you.
Hey, thank you so much. Inch pounds, and divide by 12. Get 148.9 foot pounds. Work between 1 and 2, 0. KE2 is just going to be 1/2 mv2 squared. I have this awful taste in my mouth. I know that's not information you needed, but I think it's that Paxlovid. Oh, that's awful. Let's see, what is the mass of the weight of this thing? It's a 4 pounds, so it's 4 over 32.2. That is really disgusting. Oh, no. 6.211 E minus 2 V2 squared. And potential energy when it's at here at point A, this becomes 0. So what we're left with is 148.9. So we get V2. So I just divide that and square root it. And how did I do? No. Yeah, I got it right. Okay, yay. 48.96 feet per second. Which was the answer. So, let me see. Pulling up the book in case someone wants some other choices of difficult problems. A lot of times it's good to swing a heavy baseball bat. So when you get up to the plate, instead of having a heavy baseball bat, you pick up a lighter baseball bat, and boy, it feels so much lighter because you were swinging a heavy baseball bat. And that's like when you're doing problems sometimes. Although I'm trying to open this thing up and my computer is now stalled. That's good. I wonder if you guys are still there. Still there? They look like you're still there. No, it's not working. What is wrong with you? My PDFs are mad at me. While I'm waiting for this computer to decide to open something up, anybody have a request? A type of problem or a specific problem? Want to see my dog? Come here. Come here. This would be the best part of the show. Come here. Come on. Oh, yeah. Who's a good dog? Oh, yeah. Isn't she beautiful? She knows she's beautiful. She's very vain. Just lick my eye. It's a good dog. She's a good doggy. She hates the FedEx guy. You hate him. You hate him so much. This is the best part of the whole thing, right? Oh, okay. You're taken down. Does anybody have any requests? Computer's still not on. There you go. It came up. I gotta share my screen again. Is anybody out there? You guys can still hear me, right?
Yeah.
Okay. Good. So, requests? Don't even know what to ask? They're having a barbecue tomorrow for faculty and staff, but I can't go. But I don't know what I was going to say. Let's see.
Do you know when like final grades have to be posted by any chance?
Well, the policy is that they have to be 48 hours after the final exam is given. That's what we're told. I don't know how many professors actually follow those rules. I think I've been able to do it every single time, but I know of professors who have had to who waited a couple weeks after final exams before they were able to catch up. I've heard of that. I won't name names, but it's happened before. But I think I think there was probably a semester where I had like just a confluence of events where I couldn't get it in 48 hours, but I try to. But I also think there's a certain degree of uh, lag in the system. So when I enter grades, I don't think necessarily do you see the grades that when I post them. I've seen that before where students were asking me when grades were posted and I had already entered them, but the system like takes some time to put them in. So there's a built-in excuse right there for anyone looking for an excuse. But I have been overloaded in some semesters, not this semester, but other semesters where it was just like physically impossible to grade all of the things in that time frame. Let's see, I was going to pick a problem. You know, so some of the problems at the ends of these are at the end of every chapter are kind of interesting because they have the review problems, right? So this is of the no, what did I just go to? This is this chapter 17, right? So this is the energy and momentum methods. So you take a look and try to, what is this little thing? That's a weird thing. You're asked to analyze the catcher. So challenging yourself can be a really well, like I'm afraid it could be like a little disheartening, but it could be an interesting thing to try to test yourself to see whether you are able to do a problem. It's like I'm looking at this one right here. You were asked to analyze a catcher for a small drone. The catcher weighs 20 pounds, is 8 feet long, and you can model it like a slender rod. The net that catches the drone at B has negligible mass. The 3-pound drone has a mass moment of inertia. It's got its own mass moment of inertia of 0.01 slug feet squared. Knowing that the arm swings up to an angle of 30 degrees below the horizontal. 30 degrees below the horizontal. Okay, I see what they're saying. And determine the initial velocity and the forces at that angle. The forces at that angle. That's an interesting, that last part's an interesting thing. So let me attempt this problem here. This is an impulse and momentum problem. Or, well, actually, it's a work energy problem combined with an impulse and momentum. So, this is problem 17-138. I'm doing this because you guys didn't ask a question, so I figured, hey, I mean, I'll just pick one. Why not? And we got this like little net-looking thing, and we got a little drone, and somehow I thought, somehow what came to my mind was Quidditch, right? Maybe this is what is that thing called in Quidditch for Harry Potter, right? It's I don't think it really looks like one, but somehow that's the thing that came to mind. This is 8 feet long. I'm trying to picture what this thing would look like in reality. It's 8 feet long. That's quite the thingy. And they said this thing is 20 pounds. And they said this guy is 3 pounds. And he's got an eye. Did we name him? We didn't name him. We called this point B right here, and this point A. Well, he's a drone, so he's D. We're gonna say ID. they told us was 0.01 slug feet squared. The I of B, let's actually take this about A, a little easier, right? So we know that we can go 1/12 ml squared plus m L over 2 squared, right? So we're taking it about A, makes it just a little easier. And he's 20 pounds divided by 32.2, the length of 8 feet. His mass is 20 divided by 32.2, get 4 feet. So 20, 32.2 divided by 12, multiplied by 64. Take 20 and 32.2, and take 16, add them together, and we get 13.25 slug feet squared. So they said that this thing, I didn't leave enough room to draw it up here, so I'll draw it down below. That it moves up so that it's at an angle. If I think I got that right, that says it is 30 degrees below horizontal. So this is what they mean. We should draw it with the little guy in there. So it says it's a net, so we assume that this thing has been caught right in there. So we want like, well, okay, so one thing we could do is we could figure out what the center of gravity is of the two things combined. Is there any benefit? Nah, it just kind of makes it just a little bit easier to do. Okay. So yeah, I'm looking at thinking my way through this piece. Okay, so I will say that we will call this, they decided to call that O, I'll call that there. When it gets, after it gets caught, we'll call that 1, and then we'll call this right here 2, right? State 2. So KE1 plus PE1 plus U1 to 2 is equal to KE2 plus PE2. We're trying to find KE1, and that's going to be all of the combined things together, right? So that's, let's think. I'm causing myself trouble here. By doing this, I made that more actually made it a little bit more complicated. Because what I need to do is, I just want to make sure that I account for every single thing that's here, because we now we need to also account for this guy's. I'll just put it in there, whatever. 1/2 IA omega 2 squared plus 1/2 ID omega 2 squared, but we also need to have his velocity, so he's 1/2 md vd2 squared. All right. So if we're going to do that,
shouldn't the velocity be VD1?
oh yeah, you're right. All of them should be 1s. Thank you. I'm not kidding that I have my brain is just not working. And VD should equal to omega L, right? So because the velocity here of this thing. That's after the thing has been caught, right? So they're that the anyway, sorry. So we have omega 1 squared plus 1/2 0.01 omega 1 squared plus 1/2. And let's take, he's 3 over 32.2. And so that's going to have omega 1 times 8 squared. Oh, 0.01. It's hardly even worth it. Add that in there, but 3 divided by 32.2, 2 divided, but now we're going to take 64? Really? Wow, that's going to be a lot. 64 times, I guess it didn't turn out too much. You add them all together. I get 9.612 omega 1 squared. PE1, we're going to treat that as 0. No work done. And so that's going to be 0, right? So we don't need to write all those. PE2 right here. Okay, so that's going to be let's see, the weight of AB times this distance right here that's changed right there, right? So it's going to be that distance, delta Y AB. We also need to get this distance right here, right? So those two things, because it is 3 pounds, so it's going to have a bit of a difference here. So I'll just call that delta Y AB, and then plus the weight of that times delta Y D. I'll write them over to the side. So we'll say that's L over 2 times 1 minus, I think it's going to be the sine of 30 degrees, because that's right there. So that's going to be there. Okay, yeah, the sine. Or 4 1 minus sine of 30, right? Which is just 0.5, right? So then that should end up being 2, but I can't stop myself, so I went ahead and did it anyway. Yeah. So just be 2 feet. What the hell? Oh, my office hours are starting. That should be turned off. I'm losing it. Okay, there. And then this one, not actually shouldn't be all that much difference. Yeah, well, YD is just going to be L, and then 1 minus the sine there. All right, so that's just going to be 8. 1 minus the sine 30. So PE2 is equal to the weight of this thing, which is 20 pounds, and the change in its center of gravity. And then this one's going to be 3 times 4, so 60 and 12, so 72 foot-pounds. I think I did that right. Nope, didn't. That should be. That's 40, not 60. Oh, that's why I use a calculator all the time. I can't do math in my head. Okay, so coming back to this top equation right here, we end up with 9.612 omega 1 squared plus 0 equals 0 plus 52. So omega 1, boom, 52 square root is 2.326 radians per second. And if we wanted to find out what VD1 is, that's going to be VD1. Where'd you go? That you're just going to multiply that by 8. Or 18.61 feet per second. Now we know what happens just after the thing has hit. So we do an angular impulse and momentum. And so we have this guy right here. Flying in. He's the MD V, and they just called it VO, so I'll leave it right there. But I mean VDO. So we have the equal and opposite impact that's taking place, and we have the reactions up here at A. We also had the weights if we wanted to. I could draw that as an integral thing right there, but the point is we're going to do it about this point anyway to get rid of those things. And after the fact, we're going to have IA omega 1. We're also going to have MD VD1. But you have to remember they gave it to us, so they must have had a reason. It doesn't have a whole lot of effect. Remember, because this thing is now inside this clutch, it has the same omega as the entire thing, because there's the same omega everywhere. And so we take the sum of the angular momentums about A. This is a conservation of angular momentum, so we don't necessarily have to do this right here to show it. Oof. Actually, I probably should call this 0 and 1 if I was going to be consistent, right? So this thing has M, D, V, O, and then it's going to be L because that's the distance right into there, right? We're assuming, and then nothing else coming in here is going to be equal to IA omega 1 plus ID omega 1 plus 1/2, not 1/2. Oh, I just need to get through this. All right, MD VD1, and then this is also L. So let's see. 3 divided by 32.2. VO is what we're trying to get. The length is 8. IA was 13.25. Omega 1 was 2.326 plus 0.01 times 2.326, and then 3 divided by 32.2. VD1 we said was 18.61, and the length was 8. So we're going to try to get that. A lot of numbers. numbers and numbers and numbers. I'll start with this guy here. Go 8 times that times 3 divided by 32.2. Okay. And I'll take 2.326.01 times, not a lot, we just add them together, and then 13.25. Gotcha. So this whole thing on the right hand side is 30.82 if I did that right. Divide by 8, divide by 3, multiply by 32.2. And I say that it's 41.35 feet per second is what we're estimating. Note that the thing got caught, so we didn't have to use the coefficient of restitution. If we were going to say there was a coefficient of restitution, that would be equal to 0, right? We would consider this to be perfectly plastic. Because the relative velocities were now equal to each other, right? Or I should say it the other way around, right? So the coefficient of restitution right here is, of course, would be V, I guess I have a VD1 minus, what's called VB1, because that's where it's located. That's where it's getting hit right there. So VB0, which was 0, minus V, what we called VO, right? So that was VDO, but we call it VO. But you notice that it's going to be equal to 0, right? So because it's plastic right here, so all we end up finding is VD1 is equal to VB1, right? Which is kind of what we assumed as part of the thing. So recognize the coefficient of restitution still holds true. It just wasn't necessary as part of this problem. If this thing had bounced off of it, then that would be something that we would need to include. Now the next part of the thing is a little curious to me. It wants to know the forces at A when this thing is at this angle. Well, the best way to approach that is to draw the FBD and the IBD and see what happens, right? So there's a number of things to consider. As I'm doing this, I don't know what they're getting at necessarily. All right, so we have the forces here at the pin, which I'm going to call RAX and RAY. And of course, this thing is at 30 degrees. And we have the weight here. And we also have the weight like right there, right? So we have it's the weight of the total of AB. And here's the weight of the drone. Don't think there's any other forces. Over here on this side of the thing, we are now going to, we've paused when we reach the top. When we reach the top of this swing, so it's going to start accelerating in this way right here. So we're going to have I, and we can do IA alpha, and we can consider this to be 2 right there, right? So this is actually about this point. So we don't need to use the center of mass, but because we didn't really incorporate it in there, we do need to have M of this and the acceleration of him at 2, let's call it. And then we also need, kind of idiotically, need to have this ID, yeah, ID alpha 2. And we do recognize that AD is going to be alpha times L. right there, right? So I guess we also kind of need, yeah, even though we're doing this guy, we do need to have draw the mass of AB times the acceleration. We're going to call it at G. We're going to call that point G at the center of the thing. Call it 2. Recognize that the acceleration of G is now going to be alpha L over 2. Right. I actually don't think I need the sum of the moments for anything, but maybe I do. Yeah, I do.
Dr. Deal, I have to
Okay,
go to another help session, but thank you. Have a good rest of your
you're
day.
welcome. Okay, you too. Have a great one. I'll see you at the final. So, yeah, I think the do is to take the sum of the moments about A, be the sum of the effective moments about A. All right, so that, and counterclockwise is positive, but that's going to make us some problems right there. We need alpha. That's what we're going to try to find, is to try to find alpha. Because I want to use this A right here, I don't need to double dip and do anything with this guy here within this, but I do need to account for these pieces over here. So what I'll do here, that right there is also going to be 30 degrees, and right there is going to be 30 degrees. So I'm going to say these are all negative. I'm going to take my 20 pounds and take only the cosine of 30 and take the length over 2, which is going to be 4. Excuse me. And then this guy is going to be 3 pounds times the cosine of 30 times 8, right? And that's going to be equal to I, which is 13.25 alpha 2, plus the boring 0.01 alpha 2, hardly necessary, but this will have an effect, and we will say that it's going to be the mass of this is 3 over 32.2, and it's going to be alpha times 8 squared, right? So I think, oh, and by the way, these should all have been negative. So negative, negative, and negative. So all the negatives canceled out. I was just trying to be consistent with my thing here. So 20 cosine of 30 times 4. Did I do that right? I think so. And then 3 times 8 times cosine of 30 for that one too. Add them together. So that's like, this side is like 90. For here, we're going to add 13.25 to 0.01. Then add 3 divided by 32.2, and then times 64. So that had an effect. Yeah, so that's going to be, and then we just divide it. So I think I have 4.685 radians per second squared. Now I want to have the sum of the forces in the x direction times mass equals mass times acceleration in the x direction. So now we do bring in our RAX, and you'll see that there's nobody here in the x direction except for him. But over here we have a negative, and this is the reason why I drew this on here. I know that I used this, which means I didn't have to use that in my effective moments, but I drew it on here because I knew that I needed it here. And so we get the mass of this, which is going to be 20 divided by 32.2. And now it's only the horizontal direction. By the way, that right there is 30 degrees for both of these. So we take this is going to be that alpha 4.685 times L over 2, 4, right? And then we also need this, its x component is going to be 3 over 32.2, and its acceleration is that alpha, is that an 8? That's an 8, times 8. So we're going to get in the negative direction. I drew it positive, but it's a negative. So we have 4 times 20 times 32.2 divided. I think I did that right. Swap him out and go 3 times 8 times 32.2 divided. Add them together. We get 15.13 pounds. And then do the sum of the forces in the y direction equals mass times acceleration in the y direction. I wonder if anybody's still here. I haven't checked. All right. Let's see. In the y direction, we have these guys. So RAY. But then we have minus the weight up here of this guy, minus the weight of that guy. And that's all we have on the left-hand side. On the right-hand side, we have a minus 20, 32.2, 4.685 times 4, right? Because that's the acceleration, that's the mass. We needed, I messed up. Damn. This needed to only be a cosine of 30. So I could just actually just multiply that by the cosine of 30, right? Sure. So it ends up being 13.11. So right here, I'm not sure why I'm putting it in between these guys right there. I might actually just put them into, I'll just put it next to this thing. The sine of 30. And then lastly, minus 3 divided by 32.2, 4.685, and now 8, but now only the sine of 30, right? Because it's only the vertical part of that we're doing, and those are both downwards. So RAY, so it's going to be 23, no, damn it. Let's start out here. We go 4 times 20 times 32.2 divided sine of 30 times. I think I did that right, but I don't know for sure. My head's not in this today. 8 times, let's use sine of 30. It should just put 0.5 in there. In there, and then go 3 times the 32.2 divided. I think I did that right. Add them together, but I'm going to subtract it out from 23. So I should end up with 15.43 pounds. So this is the moment of truth. Let's see how much I messed this thing up. And I've got 5 people in there. So people said 5. Let's see. Let's look it up on the solution manual and see how much I messed it up. So we have Beard Johnston, and that was problem, what, 17, 138. So it's in chapter 17. Come on. Oh, Adobe hates me. And the feeling is mutual. Drag him over to here so you can see. I need you. 138. Memorize all these quickly. 38. See how bad I did. Oh, it didn't answer the question. The force is at A. Oh, I got the wrong answer. Dang, that's not fair. I wonder what I did wrong. Yeah, it's hard to diagnose from right here. From their thing of it, they had, what did I say? Mine was, how far off am I? I predicted that it would be 41.35, and we have 60, so that's pretty significantly off. We get where is their 30 degrees coming into here? With the sine of 30. Okay, so here's their potential energy, and they decided to go negative with this, which is, we get the 52, so at least we agree right there. This is, oh, what is this 104 right here? What is that guy? Where is he from? I don't see that. Where's 104 come from? 104. He's got, for whatever reason, they have a negative 104. I don't understand that. Well, this negative 104. 3 pounds, 8 feet. Yeah, that doesn't make, oh, this is ridiculous. I don't know who makes some of these solution manuals, but what you end up with is 104, right? One half of 104 is 52. Okay. But here's a number that does not agree. I must have messed something up right there at the very beginning with my mass moment of inertia. That's what I must have done. I messed up when I went, let's see, 20, 32.2 divided, then 64 times, and then 12. Yeah, right there. Right from the very beginning, I made a mistake. So it's a simple math error. That right there. Oh, no. Okay, maybe. Oh, see, no, it's right here. Okay, so maybe I did make it. Maybe mine is correct. Well, I'm out of time. I'm out of patience and energy. I think I went through the process correctly. Honestly, I don't know for sure. I will look for my mistake and post it with the corrections and to try to reconcile them. But I'm not 100% sure they're correct, to tell you the truth. But it's a pretty good chance they're right. But don't know for 100% for sure. So thank you everybody for all the work that you've done this semester, you recitationists, and my class and other classes as well. I hope this was useful to some extent. I know I wasn't 100% on my game today. So thanks, guys, and hope you, not just hope, I know you'll do great on the final exam.
Thank you, Professor.
You're welcome. I'll post this under the on my class and in the recitation, my solution. Thank you.
Thank
again.
you. Have a good one.
You too.